Yes, actually, as I was trying to explain to you that actually I'm replacing Mauro Bologna, and I adopted the title of his talk. I don't know how much my talk will reflect what Mauro Bologna had in mind to illustrate to you, but I decided uh, to work as a bridge between what Bruce West has been telling us this morning when he talked about the complexity meshing, and the talk that will be done after me by Kurus Mahmoudi, which is a work that he did together with Scott. And also, I would like to establish a connection with something that will be discussed, I don't know, tomorrow, and about biophotons, and especially something that will be discussed in the afternoon of Saturday. So let us move to the second slide, please. So what I'm doing here is a very tutorial introduction to the concept of crucial event, let's say, and the origin of our approach to complexity is the work done by Prakash and Schuster in 1983. The many other people, by the way, there is a large list of people that have been studying turbulence, and you see there is that equation, yn plus 1 equal to y of n plus constant multiplying y of n to the power of z, that is a number larger than 1. Actually, we decide to make the computational approach faster. I decided to replace that map with an idealization of the turbulent map that is essentially totally equivalent from a point of view of complexity to the original map. So is given by the equation y dot equal to a y to z. I think that Bruce, in fact, this morning showed this equation to the audience. And let us move to the next slide, please. So what you have to do is this. You have I'm essentially repeating what Bruce already told of you. Is you select you assign it to the variable y move in interval 0, 1, and it will move from a given initial condition y, and in its motion it will move from y to, which is initial condition, to 1. When you reach 1, there is a batch injection, which is totally random with equal probability. So this very idealized map is essentially has the same complexity as the turbulent map invented by many people, Prakash, Schuster, Maneville, many others. And then analytically, you can prove that, so which are the crucial events? When the particles get the value 1, it is injected back, and then it's injected, then it moves again towards 1, and the time distance between 2 times at which the particle reach the value of 1, that time distance is the time distance between 2 consecutive crucial events. And it is very simple. It's given by the equation tau equal to big T. Big T is mu minus 1 divided by A, which is a parameter of the idealized map. And it depends on 1 over y to 1 over mu minus 1 minus 1. And mu is 0 over z minus 1. you can run it as essentially you don't have to run a map. You see, you have for any value y that is supposed to be obtained with uniform probability, you get a value tau. And please go to the next slide, slide 4. Yes, and what I would like to do is I would like to focus on, it is easy to prove analytically, that's totally analytical, that the waiting time distribution, the time distance between two crucial events is an inverse power law with tau to mu, and mu go from 1 to infinity. So there are two values, mu equal to 2 and mu equal to 3, which are very important. And Mauro Bologna did something very important, very good. He studied what happens in the region between 2 and 3. And so the region between 2 and 3 is an intriguing region because according to the research work that we did examining the human brains is essentially the region where the dynamics of the brain is located. And that's why it's very important. And but that region is also the source of big confusion because while the mean value of tau for mu more than 2 is divergent, which is the region that he used to call the region of perennial aging, the value of tau, the mean value of tau between 2 and 3 is finite. It's given by big T divided by mu minus 2. And the fact that it's finite is a source of big confusion. There is a big, what is the big confusion? The big confusion is that often this kind of dynamics is confused with a very popular theory invented by Mandelbrot, which is the fractional binary motion. And there is the big confusion is the fact that there are many processes that are generated by crucial event, and they are interpreted as due to the Mandelbrot theory. Well, it is what I'm going to show is the fact there is a big difference between the two perspectives. By the way, I would like you to realize that the big psi is the survival probability, and the connection between the small psi and the big psi is that the small psi is minus the derivative of the big psi. And let us go to this next slide. So in the next slide, I am doing something that I'm going to reproduce the same waiting time distribution, the same the waiting time distribution and the same survival probability using a theory, a renewal theory invented by Sir Cox. So Queen Elizabeth made him Sir for his big merit in science, and which is essentially what Cox did. He imagined that when you have you create a new machine at time t equals 0, if the machine becomes older, and so g of t of g of t tend to increase, the agent there is g of t is the failure rate, and the failure rate is expected to increase for a real machine, and is defined by the ratio of the small psi to the big psi. Since the small psi is minus derivative of the big psi, it is easy to prove that the survival probability is written by the bottom equation, which is can be easily solved if you know g of t. If you go to the next slide, slide 6. And you see, now you make an assumption that seems to be extremely strange, very strange. So you imagine a machine that where g of t, rather than increasing in time, and by the way, human beings are machines with the g of t that should increase exponentially if you want to reproduce what happens. So if you want, you want to do a model that is good for insurance companies, but you can imagine a machine where g of t, rather than increasing exponentially, tend to decrease in time, and as 1 over t. That means you are at the border of integrability. It is a very simple exercise to prove that the big psi the survival probability has exactly the same form as the one that we found using turbulence. And R1 is equal to 1 over t, and mu is 1 plus R naught divided by R1. Here you must say, what a strange model. Actually, is what I'm trying to show to you, that this might be a very good model to explain the behavior of the brain, but which is the intuitive interpretation. So the fact that g of t, rather than increase, being constant, means that you have a Poisson process. If tend to increase to reproduce what really happens to human beings, but if the fact that it decreases is a consequence of the fact that you are talking about a system of interacting units, and those interacting units might, as a result of a process of self-organization. So here I am also introducing in an intuitive way the process of self-organization, tend to produce the fact that the failure rate, rather than increasing, tend to decrease in time. And that's our interpretation of the formula that I gave you using turbulence. Go to slide 7. And now, you see, I am trying to establish, I am to introduce to you the result that Scott and Kourous got recently, a work that is not yet published, which was mentioned by Bruce this morning. But I'm trying to explain why which is the origin of the surprising result that they got. And to explain that, I have to go back in time to 2013, where you can see Mauro Bologna is one of the authors of this paper. What is this paper? This paper is based on the assumption that the crucial event, we call crucial event the time at which the particle y reaches the value 1, are not visible. So you can imagine that the probability of detecting and perceiving the crucial events is p subscript s, and p subscript s is a number extremely small. What we found in this paper published in 2013, we proved in a rigorous way, introducing a kind of generalized central limiter, we proved that the big psi that let us call that the big psi that the turbulence theory or Cox theory led us to that big psi. Well, that big psi, if many events are invisible, because the probability of detecting them tend to 0, the big psi becomes a Mittag-Leffler function. Well, so if you read this paper, you can find the theory, you can find the theorem, and is a kind of central limit theorem. But to give you an intuitive interpretation, if you have a Mittag-Leffler function, you see that the Mittag-Leffler function for t tending to 0 is a stressed exponential. And then that stressed exponential is followed by the slow tail 1 over t to alpha. Alpha is mu minus 1. So, which means that you need to have mu's more than 2. And lambda is related to the big T of the turbulence theory by the bottom expression. You see that for PS tending to 0, lambda tend to become smaller and smaller, which means that the stress exponential becomes lower and slower. But the problem is that there is something impressive here, that even if you study t tending to 0, you get information about the complexity, because you have a stress exponential, you have lambda t to alpha. Alpha is mu minus 1. You have an information about mu. Also, if you use a time series that is extremely short, because what happens is the fact that as a result of making the crucial event invisible, you create a time series that is much more extended. Then you have to squeeze the time and to generate something that you can observe. And then you have this impressive effect that even if you send t to 0, you have information about the complexity of the process. Now, let me see if I go to the next slide. Yes. What it is possible to prove is the fact that if mu is larger than 2, so you don't have the alpha of Mittag-Leffler function becoming larger than 1, because the Mittag-Leffler function generates a kind of infinite memory for alpha larger than 1. But you have to remain at the level of crucial events, and it is possible to prove that also in the case where mu is larger than 2, as a result of creating many invisible events, you have a big T tend to become extremely much larger, and what you have now is what is the benefit that you can get? You can observe time series. So this is a work that I don't know if Kurush will give you details of what he did with Scott. They analyzed, so what is this figure has to do is the observation of many different areas of the brain of the same individual. And you see that delta, which is the scaling, is synchronized. So there is a synchronization of delta. Now, let me tell you why this result is impressive. Don't have to confuse that synchronization with the very famous chaos synchronization that it was invented by Pecora and Carroll in 1990. You have a scaling synchronization. What is the difference between the chaos synchronization of Pecora and Carroll and the scaling synchronization? That the scaling is a property is not a property of a given time. To evaluate the scaling, what you have to do, you have to take a signal, you use that signal to generate diffusion, and then you have to use a generalized central limit theorem. So if you use the ordinary central limit theorem, you get delta equal to 0.5, which is the result of Wiener mentioned by Bruce this morning. But if the process is complex, you'd get a delta that is different from 0.5. But you see, if you look at this figure, you see that delta is in fact moving. 0.5 is the minimal value, so to speak, and there is a change from 0.5 to values that are 0.75. And what is impressive is the fact that all the channels explored by Kourous and Scott are you could evaluate the scaling, and then there is a scaling synchronization. The scaling synchronization is, in my opinion, is a very, very exciting result. I am extremely impressed by this result, and let us see. I will try to make conjectures about what might be the consequence of this impressive result. Let us go to next slide. I don't know if Paolo Allegrini, that this morning made a question to Bruce, and I was very happy to meet Paolo Allegrini after many years. He made a question, interesting question, and so in order to explain the importance of the result of Kourous and Scott, I need to make a jump back in time to the year 2010. This is a paper. I would say I'm very, you see, I miss very much that time. It's a very exciting time. And Paolo Allegrini, Paolo Paradisi, Danilo Menicucci, Angelo Geminiani made a very important discovery. What is the discovery? Let me tell you that I know that I remember that Danilo Menicucci wrote his PhD thesis with Rita Balocchi, and on the empirical mode decomposition. And I remember that at that time I was telling him that yes, empirical mode decomposition is very interesting, but there is something more exciting, which is the fact that the brain might host crucial events. How can you detect crucial events in the brain? And Danilo Menicucci made a discovery. He found that the Finkelkurt brothers, under the direction of Mr. Kaplan, Kaplan from Russia, and the Finkelkurt brothers immigrated to Finland. They found that the brain EEGs are characterized by what they called rapid transition processes, RTPs. And unfortunately, I couldn't reproduce this figure. I'm sorry. I did my best. The figure that you can find in the paper of Allegrini and his co-workers is extremely nice, because you can see that in the region that they explored of the figure, they found, I think, 14 or 15 rapid transition processes. And when they found that, I asked them to check if these rapid transition processes are crucial events, in the sense they should be renewal, they should obey, they should generate the aging that David was talking about this morning, and quite surprising, we were very, very excited when they proved that that really so. So in other words, the rapid transition processes are crucial events. The problem is, however, it is that there are only a few. And if you want to generate, you want to get the result that Kurus found using a sequence that, so what Kurus did, he took the data, I don't remember the length of the data, suppose 10 minutes, and then he decided to split that into small pieces of 1 minute. And then in 1 minute, he found the scaling. But the scaling generated by crucial events requires many crucial events. How can you find that impressive result? In fact, I had asked one of the students of, well, former students of Center of Linear Science to do the calculation, focusing on the rapid transition processes, and he didn't find. So if you have a large time sequence with the scaling delta 0.7, and you examine only 1 minute, you don't find anything. While Kurus didn't do that. Kurus examined the data as they are, and it is evident that the result that Kurus found is due to the fact that there are many invisible crucial events that the rapid transition processes of the Finkelkurt brothers are only some of them, which that means also that well, here I should spend much more time, but I don't want to let us see, go to the, it's almost done. I think that I wrote 12 slides, so you are almost at the end. Let us go to the next slide.
Sorry to interrupt you. You have 2 minutes actually to conclude.
Oh, 2 minutes? Okay, right. Okay, go to the next slide. And I think that there is, yes, now I would like to mention a very important result of Mauro Bologna, that he did what Mauro Bologna did. He invented a method of analysis that is essentially is based on this waiting time distribution with mu between 2 and 3, and he generated a diffusion process, and then to find the probability px of t, he invented a method based on two Laplace transform with respect to time and Laplace transform to the space, and he got an exact result. The formula of Mauro Bologna is exact. I don't show the formula here, but what he did is he examined the central part of the distribution, assuming that the process, there are crucial, there is a Lévy statistics, so which correspond to mu equal to 2.5 in the formula that I wrote, and they found an impressive agreement. So, in other words, Mauro Bologna found an exact analytical formula that is characterized by Lévy statistics. This might be, I don't think, I think this might have some interesting connection with the work that Marco Ganucci will be talking about in the next few days. And let us go to slide 11, because I have only I don't want to exceed my time. Go to slide 11. Slide 11. Okay. Slide 11 is something that I would like to stress, which has to do, you see, the region explored by Mauro Bologna is the many authors interpret as a form of fractional motion, but fractional motion does not have a crucial event, no crucial event at all. And what we found is you have two papers. One is the paper of Jelinek was done examining the heartbeats of people under the influence of autonomic neuropathy, and we found that at the beginning, when they are still healthy, they have crucial events, and as a result of the increase of severity of autonomic neuropathy, they generate fractional biomotion. Then there is another exciting result found by experimental work done by Maurizio Benfatto and his co-workers, which shows that the germinating seed generate arc. So when you are water a germinating seed with to produce germination, then there are crucial events, and as the time goes on, the regime is characterized by the Levy statistics is changed into a Gaussian regime. So here you have something that it was a conjecture made many years ago by Paolo Allegrini. I hope that he's listening, that the fractional motion is generated in this way. First of all, there is a self-organized temporal criticality that generates a temporal an anomalous scaling, and Levy statistics. Then, as a result of the disease, Levy statistics is cancelled and is replaced by Gaussian statistics. And at that point, if you are a human being, you are going to die. And if you are a seed, don't know, it's not yet clear what it is. It's not clear if the result of Maurizio Benfatto or a sign of the stress that he is producing, keeping the seed in a dark cavity, or it has to do with the fact that the vegetative dynamics is different from that of human beings. Okay, I tell you that you go to the next slide, which is the end. So I would like to thank you very much for listening to me.
Thanks for your contribution. Let's thank the speaker. We have time just for a very short, brief question, if anybody has.
Well,
ciao Paolo.
There a question?
It's the only time where the guy that should
Paolo
to the question that you made.
Okay. But you are Paolo Allegrini?
Yeah, it's me.
Very nice, very nice. I thank you very. It's very nice for me to meet you.
We have to be very. We have to be very. I will be talking about something, and I will put the answers on my talk on Saturday morning. And what I wanted to say is that our recording were much longer than 10 minutes. Actually, we also had a few minutes recording. We had many events. They looked crucial, but probably not all of them were crucial. There were also pseudo events, and probably there were also invisible events. We discussed that years ago, and the problem, we should go back to that. Yes.
Yeah, absolutely. Yes. I think that Saturday might be devoted to that issue that is very important. Of course, there is another issue that I would like to talk about, the philosophical part.
I'm sorry, I have to stop you here.
Okay. Yes. Okay. Fine.
Thanks. Thanks again. Let's thank the speaker again.